So let's go ahead and get started. So what I'll talk to you today, my talk is, I have a lot of slides, but I will say that if you have any questions throughout the whole talk, feel free to interrupt me and I will do my best to explain something or explain something more or anything. Like, please feel free to interrupt me. But I do have a lot of slides. So hopefully it's exciting. I will try and get through it. I did try and go through a lot of some of the math behind it, and then I can kind of speed run some of that and get to the really cool stuff. If anybody's really interested in math, I can go into more detail, a whole bunch of stuff. So I'll give an introduction to interferometry. I'll talk about the interferometer that I work with, which is called Chara, and then I'll go into a little bit about my research, and then also the other applications of optical interferometry. So for context, I will be referring to interferometry because it is a mouthful, and it's even more of a mouthful to say long baseline optical interferometry several times throughout this talk. So I'm going to, from here on out, I'm going to refer to as LBOI. So just a heads up. Okay, so introduction to interferometry. So interferometry is a measurement method using the phenomenon of interference of waves. And there are several different types of interferometers used. I'm sure everybody here has heard of LIGO. We have the microsync interferometer. So LIGO is an interferometer. It's a different type of interferometer than what I use, but the microsync interferometer here, and hopefully I'll try to stand on the way so everybody can see here. This is the basic concept of pretty much, it's the foundation of most interferometers in use today. This guy was an absolute genius, and he actually worked at Mount Wilson Observatory, which is where the interferometer that I use is located. So it's really cool. It's very small world that astronomy is. But we have microsync interferometer, and so a little brief description of this is that you have a light source and you have two mirrors, something called a beam splitter, and what the beam splitter does is that it does exactly what it says. It splits the beam. So you have a light source coming in here. It goes into the beam splitter. It gets split into two parts. One going to mirror one going to mirror two, and then the mirrors reflect them back into the beam splitter, and then the beam splitter recombines the beams and sends it to your screen. And so if you have mirrors that are, they're not at an angle, you're going to get a cool little pattern that looks like concentric circles. But if the mirrors are slightly off axis, you're going to get this kind of fringe pattern here. And then you're also going to get some reflective sources here just because of mirrors are not 100% perfect and so on and so forth. So microsync interferometer is it's the foundation for most of the interferometers that we have in use. So with interferometry and astronomy, there are several different types. We have radio interferometry, so we have the cleverly named Very Large Array. I love astronomy because our acronyms make very perfect sense, or they make great sense. So we have the Very Large Array, there's ALMA, and then of course we have LIGO, one here in Livingston, Louisiana, the other one in Anchorage, Washington, and of course the Virgo-Packer collaboration. So LIGO is an insanely long, very, very big interferometer, but it does very different things than the optical astronomical interferometers. And we have optical astronomical interferometers. And so here pictured are the three main ones that are in use today. These are the ones that are generally, they're used the most. There are other ones that exist, but these are the powerhouses right now. So right here, this is the Chara array. Here is the VLTI, or the Very Large Telescope Interferometer. Once again, astronomers, genius namers. And then this one is the Naval Precision Optical Interferometer, or NPOI. VLTI is located in Paranal, Chile. It is run by the European Space Agency, or European Southern Observatory. Lots of acronyms, that's something I say all the time. And then NPOI is in the U.S. I just forget which state. I'm pretty sure it's in northern Arizona, but I could be wrong. Don't quote me on that. But Chara is located in Southern California, on top of Mount Wilson.
Am I blue to do that?
Surprisingly, no. So I've actually been to, I should have put pictures up here. I cannot believe I didn't do that. I've actually been to Chara, and you would think, being right outside of LA in Pasadena, and we millions of people, you'd think that there would be a ton of light pollution, but actually the marine layer that covers the city at night blocks out almost all of the light. And so I actually, when I got to go observe, when we were heading back to our cabin, we were heading around sunrise, and we got to see just like overlooking LA, and it looks like an ocean of clouds. It does, you can barely tell that there's a whole city with only people there. So Mount Wilson is pretty high in elevation, and there's already an observatory up there. There's already the foundation. Actually, a lot of historical interferometers were built actually at Mount Wilson. The actual first use of the stellar interferometer was at Mount Wilson Observatory. It was actually used by Albert Michelson to measure the size of Betelgeuse. So Mount Wilson is a very historical site for interferometry. It's really cool that I get to kind of work with this array. But yes, light pollution, not a problem. Very, very surprising.
Do they still use 112?
I don't know if the 100-inch is in use. We use different telescopes. So here is the 100-inch right now. This is the dome for the 100-inch. This is one of the other telescopes. But you can see this tower here, this tower here. There's a little dome here, and there's like the others that are hidden. Those are the telescopes that are used. Okay, cool. How does it work? All right, so I can't really talk about interferometry without talking about light, and it's quantum nature. I'm sorry. It is both a particle and a wave. So, way back when we had Sir Isaac Newton saying, oh yeah, light's particles, light is particles, light is particles. But then this guy here, I'm going to mispronounce this guy's name. He says that no, actually light is made up of waves. And this led to Thomas Young's very famous double slit experiment. So his experiment, something that I hope we're all aware of, if not, it's okay. This is just really like hammered hard into our brains during optics. He proved that light is a wave. So essentially this gift here, you take something like a sheet of tinfoil, a piece of paper, whatever you need, and you put 2 holes in it, or you have 2 slits, hence the term double slit, and you shine a light through those through the 2 holes. But you don't shine, you shine one light through it, and actually instead of just light being just 2 kind of shadow or 2 light spots being and the rest being in shadows, that didn't happen. There's actually this interference pattern that you can see here. So you have this plane wave, this regular light going through, and then as it's going through this hole, it splits and it starts to combine with each other, and it demonstrates the theory of superposition, which describes how light waves are combined. So you either have constructive interference, which produces those light spots that you see right here. So there's these light spots and these dark spots here. This is when the peaks of the waves add together. And then the dark spots are the destructive interference, and that is when they subtract from each other. So this experiment was insanely successful. It blew the minds of all the optical, the physicists, the astronomers, and it is the concept of superposition and interference is the key ingredient to interferometers. No matter what type of interferometer you're thinking of, whether it's LIGO, whether it's ALMA, whether it's CHARA, whether it's, you decide to build a Michelson interferometer at home for some reason. I mean, if you can, that's awesome. They're really hard to align, but key ingredient of interferometers. All right, so astronomical interferometers. I mentioned a few of the radio interferometers, the LIGO array. LIGO does study astronomical objects, but you don't really consider it an astronomical interferometer because of its nature, and because it uses a laser as its light versus astronomical interferometers, which use starlight as its light. And so the most basic form of an astronomical interferometer is shown in this diagram here. And I'll have a bigger version of this, I'm pretty sure, in the next slide. So you'll have 2 telescopes, and they're both looking at the same star, and the light is collected, and then recombined in the lab, and then you get a pattern. So most interferometers now, or astronomical interferometers nowadays, are actually not just 2 telescopes, they are multiple telescopes. The math behind that is still something I'm struggling to understand, because we go from some math that I'm pretty sure I get, and I'm pretty sure I understand, and I could derive, And then you add another telescope in there, and I'm like, I'm tapping out. I can't do this. But it's absolutely amazing what they can do, and the reason why you want more telescopes is to, I'll show you some examples of some of the pretty cool science you can do with more than two telescopes. Well, why do we care? Why do we want multiple telescopes? Why do we want to use an astronomical interferometer? And that is because of the concept that I hope everybody here is familiar with, and that is resolution. So we all should know that resolution is defined with just a regular old telescope. It is defined by the size of its primary mirror or its primary lens. Now, unfortunately, telescopes are really expensive to make, and if you want a really big telescope, it is very expensive, and actually it gets to a point that it physically cannot happen because it would be so big that gravity would take over and crack your mirror. That's why the James Webb telescope was segmented. Instead of having one big massive mirror, they did the however many mirrors exist. It's physically impossible to have a telescope that big. And so what they came up with is that instead of having one really, really big telescope, let's do a couple smaller telescopes, place them the distance apart of the size of the telescope that we want, and boom, you get the same, you get the same resolution. Now, the difference between having a single telescope, say for example, I'll use Chara as an example. You'll probably hear this fact again later on in the Chara slide. Chara's resolving capability is the same as if you had a single telescope the size of a mountain. And that is with 6 telescopes, 6 1-meter telescopes, so small telescope, relatively small, but with its maximum baseline, it has the same resolving capabilities as a telescope the size of a mountain. Like, that is insane. And so that means you get some really, really crazy resolution. And so that is it. Interferometry is just insanely powerful because of that. Now, to caveat that, it has the same resolving capabilities, but not the same light collecting area. So because it is, instead of one massive 330-meter mirror or lens or whatever you want to use in your telescope, it is 1 meter of mirrors. And so it does not have the same light collecting ability, but it does have the same resolving capabilities. So that's always the little caveat we like to say. So with a single, the resolution is set by the size of its mirror and diameter, or the mirror lens, and then with an interferometer, it's set by the baseline of the array. So just how far apart the telescopes are. So this is the setup here. We have 2 telescopes. It's observing the same star. They're separated by a base. Oh, sorry about that. No spoiler. Baseline B. The light from each telescope is sent along some mirrors into our optics lab. It's recombined. And the reason why this light here from this telescope is sent into this optical pathway compensation, or just the optics lab, is because the light, or the starlight hitting this telescope, hits this telescope at a different time than it hits this telescope. Light moves really fast. I know it's hard to think about, but we do have to account for the fact that because they are separated by this baseline, the light here will hit this telescope at a different time, so we have to bounce the light around a couple times in our optics lab to have it arrive at the instruments at the same time as the light from the light telescope. And that concept is called delay, which is given by E times sine theta. Okay, so what is observed? Astronomical interferometers are not just looking at stars. So when you're taking data with an interferometer, you're not looking through a telescope and just seeing, pretty stars or the moon or anything like that. You can see the star, it's just a dot of light. It's not really all that impressive, but the data that we're taking, the things that we're seeing and trying to achieve are called fringe patterns. And so the interferometers produce, the recombination of light produces these patterns. This is a very idealized fringe packet. They don't really look like this when you're actually taking the data. They're actually much messier than this, but that is the story of science. But the cool thing about this is that by just observing one star with 2 telescopes, there is an insane amount of information encoded within these parameters. I could tell you the size of the star, the shape of the star, and if their star has any surface features. And that is on a single star, not a bunch, that you're not seeing a lot of stars, you're looking at one single star, and we could tell you the size, the shape, and the surface features on that star. That blew my mind when I learned about this. And so how we can do this is using a concept where we take the contrast of the amplitudes of the fringes. We call this visibility. This is the very simplistic version of the equation that we actually use. And I'm going to very quickly go through the math. Sorry, everybody. Hopefully this is interesting. So how does that work? How do we go from this, and we're looking at these, to getting any sort of information out of it? Well, we like to go to our handy-dandy E&M equations. And we use the real part of the electric field. And so you start with the real part of the electric field equation. And then you have your IUIs, interferometer. Interferometers are not this simple. There's more than one telescope. Light is not monochromatic. There's a whole lot of caveats here. But the simplistic version is actually pretty decently close to the actual complicated version. So you have two telescopes separated by a baseline of B, you have some starlight coming in, you have some delay that each light has to take, and then it has to get into that beam combination. So start with that real part, split it into two because we have two telescopes, so we need two equations. So you take that electric field, split it, assign some arbitrary coordinates, you have x1, x2. All right, we did that, cool. But now we need it in the same coordinate, we need the same variables in the equation. So we replace x2 with b equals x1 because b baseline equals the position x1 plus position of x2. So you do some more math, and then you do more math. You can absorb some terms into a normalization factor, throw another Greek letter in there, and then you want to send these beams. So now we've described the light waves coming from the two telescopes. Now we want to send them down those path lengths. So we send x1 beam down this delay line B1, and then we send x2 down the delay line B2, and we get these lovely equations. All right, not too complicated just yet. Just wait.
Question.
Yes.
Why is there an approximation symbol like P1?
So I use the approximation symbol because I am not including some of the normalization factors and some of the constants because to make the math cleaner and prettier on this. Yeah, no, it just means there's some stuff not here that it doesn't need to be included right now. All right. So I told you that superposition, we like to combine the light. So we combine the fields, we just add them together. And this equation pops out after you do some fun math. So now we are in the beam combination. So awesome, we have the description of the electric field, we have the equations of the electric field for the real part of the light waves that just hit our telescopes, and we send them down the delay lines, and now we're in the beam combination line. Okay, now what? Can't really do much with this just yet. So we like to square it. We like to take the magnitude because the magnitude is very powerful. It will tell us the amplitude of the fringes. And like I said before in the previous slide, the visibilities, which is what we call interferometric data, is the contrast of the amplitudes of the fringes. So we need a way to get the amplitudes. So we take the magnitude, do a lot of math, do some substitutions with Euler's formula. I had to look up a bunch of Triggs identities because I always forget them, and that's always a tab open on my laptop. And then, of course, add in a scaling factor, redefine a few things, and essentially you want to get it into a form that looks like this. This equation, which is P equals 2 times capital A times capital F times 1 plus cosine of KB. This describes the incident source flux power at the collecting area of the telescopes. So this describes the power or the flux received essentially in the beam combination lab. There's a lot more physics, there's a lot of math. This took me maybe 10 pages of kind of paper to work out, and I made a lot of mistakes. I had to redo this, but I wanted to make sure I do this for my general exam. or my thesis about it, and it really took a while. So we have this equation. Cool. We still can't do too much with this because this is just telling us, okay, this is the amount of light we're receiving at this telescope. This isn't really cool that all right, we have this amount of light. Now what? Now what can we do with this? Well, after we get this power equation, we then need to do some coordinate transformations. We also need to assume that we're not working with monochromatic light, and we're also not working with things that are completely perfectly on axis because we're on a quick, so the world is not flat. We're also not working with idealized situations, and so we have to do a lot of finagling there. We have to do some coordinate transformations, and so this is after a bunch of coordinate transformations and removing the monochromatic light and polychromatic light. We throw an integral in there because once again, it's polychromatic, not monochromatic. We also need to, what this equation tells you though, and this is what's really important with this kind of math, is that it tells you that there is a brightness distribution, which is the F alpha beta, that you can take and you can apply known brightness distribution, and you can plug those into this equation. And the reason why we want to do this is because of a theorem called the Van Sittert-Zernecke theorem, which tells you that the power response of an interferometer is the Fourier transform of a brightness distribution. So lots of math words that I'm still it takes me a second, I have to sit down and actually read it out and see it, and then it makes sense to me, and then I immediately forget it when I'm not thinking about it. So essentially, what you want to do here is that you want to figure out how you want to describe your object that you're looking at. If you're looking at a star, you can choose pretty much two options here. You can do a uniform disk, meaning you have just a disk which is completely the same brightness all the way across. You could say it's a point source. You could also say it is a limb darkened disk, which means that the brightness all across the star is not uniform. So if you look at, let's see, you guys have plenty of pictures in here. I don't see the one I wanted to replicate up here. There's a picture of our sun where at the center it seems much brighter, and as you move out to the edge of the star, it gets darker. That concept is called limb darkening, and that is because the stars are not constant. They are, the surface is not, it's a function of opacity, of temperature, of surface gravity. It's a lot of more physics is going into it. I could probably spend another 3 hours talking about that, but you have to take into account that. And once you figure out what kind of brightness distribution you want to do, you throw it in this equation, you do some Fourier transforms, you do a lot more math, a lot more integrals, and then you get this equation. This equation is extremely powerful. So I'm gonna zoom back a few slides really quick. So I told you that this is the equation for visibilities. This is the true equation for visibilities. So this equation is a lot to unpack, but it is a very powerful equation. So this is the visibility, and you'll notice the visibility squared equation, because way back when I didn't include this, we have complex terms. And unfortunately, when you have complex terms, you can't really do much because they're not real. So you need to get rid of those, and you do that by squaring. And you can get rid of those complex terms. And so what this equation shows you, and this is the equation that I use in my research, and not a lot of people, this equation is used pretty much by any person doing optical interferometry work. What this is a function of is we have this mu here. That is the limb darkening coefficient. So that is just some number that will describe the amount of limb darkening that's going on in your star. And then you have this x term. This x term is really, really cool. And I know it's math. Is it really that cool? It is, I promise. X stands for pi times theta times b over lambda. Now, when you have an optical interferometer, you know what b is because you know your baseline, because b is your baseline. You know how far apart your telescopes are. You also know lambda, which is your wavelength of observation. So if you're observing in H-band, you know your wavelength. So all that's, and we also know pi. Pi is very long. So the only thing that you don't know in this entire equation, this entire complicated equation, made up of Bessel functions of the first kind, and then like 2 and 3 halves, and then you have some squared terms, you have a bunch of stuff going on here. Out of this entire equation, the only unknown is theta. And theta is your angular diameter of your star. So when I tell you that by taking interferometric measurements that I can tell you the size of the star, this is how. So by taking visibility data, taking interferometric data, I take it, I make a plot, because astronomers love our plots, and I fit this equation. And it's not as complicated as you might think, because you know mu, you know v, and you know lambda. You're just fitting for one variable, and it can tell me my angular diameter. And it's even more crazy because when you first start out, you want to do a uniform disk fit, meaning you set u equal to 0, which means that goes away. And no, this doesn't go away. That won't go. So this doesn't go away, but all of this goes away. So you have some constant. You have 1/2 plus 1. You have 1/2 times j1 of x over x squared, and that is how you get your uniform disk angular diameter. And then once you figure that out, you do some more math, do some modeling, then you can get your wind-directed angular diameter. And so interferometry is an incredibly powerful tool because it is one of the only direct methods of measuring stars and just objects in the sky. Yes?
Can you explain what a function is again?
It is a Bessel function. So this one is a Bessel function of the first kind. So it has to do with a bunch of Fourier transforms. I cannot remember the math off the top of my head. But if you just look, if you want to know more, just Bessel functions. So interferometry, there are a few ways to directly measure stars, and all of them are very difficult to do. One, you need an eclipsing binary. Not all stars are in eclipsing binaries. You would want to do astroseismology, which is a whole other complicated term that you would need to still observe the star. You can also do lunar occultations, or just occultations in general, but also the chances of that happening all the time, not very common. But then you have interferometry, where all you have to do is just look at a star, as long as it's in magnitude, or in the magnitude limits. You can look at it, you can get some data, and you can directly measure the star. You can literally hold a ruler up to your star and get you can get a direct measurement that is completely model independent. You're not relying on any physics of the star. You're not relying on stellar evolution. You're not relying on anything to tell you, like, oh, well, if we assume that the star is made up of this much hydrogen and this much helium and this much whatever, and it might be this old and this heavy, then maybe you can do a bunch of like finagling calculations and you think it could be this stuff. No, you just observe it with a couple of telescopes and you figure it out. That's insane. That is so cool to me. Blew my mind when I figured this out and it clicked, and it was awesome. I fell in love with interferometry. Hopefully you can tell. Okay, so now that I've kind of talked about the math, I'll talk a little bit about CHARA. So CHARA stands for the Center for High Angular Resolution Astronomy. It is run by, the main group that runs it is Georgia State University. It's a consortium, so there's a couple other universities that are involved. University of Michigan Ann Arbor is one of the really heavy ones that have been really involved in building CHARA. So it's located at the Mount Wilson Observatory on Mount Wilson, California. Its maximum baseline is 330 meters. Its best resolution is 0.2 milliarc seconds in the visible, and 0.5 milliarc seconds in the near infrared. For context, Hubble is not this good. James Webb, not this good. But I will say, caveat, of course, we can't get the really pretty pictures. We can just resolve individual objects really well. And I will show you just how well we do that.
The atmospheric problem interfere with the
So because they are ground-based telescopes, there are some atmospheric issues, but I will say that most of the time, the way that we take data with an interferometer, it gets power in it out. So how you take data with an interferometer is that you have you should have at least 2 calibrator stars. The calibrator stars should be close in magnitude and close in distance, or they should be relatively the same distance away, similar position in the sky, and that's mainly just so you don't have to slew your telescopes all over the sky. and you observe a calibrator star, you observe your target, and you observe another calibrator star, and that kind of chunk of data is called a bracket. And the ideal, like the minimum requirements when you take observations is you should do minimum 2 nights, minimum 2 brackets, minimum 2 baselines, minimum 2 calibrators. And that is because if you have data taken on multiple nights of different stars, you can really get the instrument responses, you can get the atmospheric issues, you can get, like make sure nothing like weird is going on with the telescopes, and that all can get calibrated out. So also another really cool thing about this. And in general, most of, when it comes to just working with stellar diameters, which is what I do, atmospheric conditions, not really a problem for us. We just need to get enough data on a curve to fit that curve. If you want to do some other stuff, like I'm not going to spoil it, you'll see what I mean in a couple slides, but some of the other things that you can do with interferometry, it does kind of rely a little bit more on the scene, just because of the nature of what they're doing. So this is the actual picture of Tara. This is just an easier one to kind of see how everything's laid out. So we have 6 telescopes arranged in a Y formation. We have S1, S2, E1, E2, W1, W2. This is our beam combining lab and the synthesis facilities. So this long part of the L here, this is where our delay lines are. So it's basically a bunch of traction mirrors that move up and down throughout the night. In the short part of the L, that is where all of the instruments lie. So it's a big room full of a bunch of optics tables. And then of course, like we have, this is the 100-inch telescope. There's the 60-inch. There's a few other. There's the solar. There's a whole bunch of other stuff here. Because Mount Wilson is still an active observatory. We're just there. And so Char also has 4 active instruments and 2 additional in commissioning. Technically, that's 1 in commissioning, but I don't really believe that one of the instruments is actually working properly. So the ones that really matter to me, I know these don't look like much, but these are what are taking. This is what's taking our data. So this is very blurry. This was straight off the website. This is not me, so I apologize for the quality. This instrument is called Classic. It is a 2-beam combiner, and it operates in the near infrared, so it operates in H and K band. We have Pavo. Pavo is what most of my thesis data came from. It is a 2-beam combiner, and it operates. You get this invisible, crazy. And then we also have Vega. Vega is a 2-beam combiner, also operates invisible. And then there's Merc X, and I want to applaud whoever set this up because this is very pleasing to the eye. You can tell someone with a lot of time and they're very, very particular about what they do. In fact, I know the person who set this up, and it's very true. Merc X is it's the developed by University of Michigan and the University of Exeter. It is 6-beam combining. It can combine up to 6 beams. It can do a combination of all 6. So you can do 2, 3, 4, 5, and 6 if you would like. And it operates in the near infrared. And there's also another instrument kind of attached to the Merc X called Mystic. It's the same instrument, it just has a different name and it operates in a different band. Okay, so a little bit about my research. I know I'm kind of yapping on, but hopefully you guys are still interested. So what I do is that I study exoplanet host stars. Exoplanets are really fascinating to me. I was able to intern with the test team several years ago, and I just fell in love with exoplanets. And I am now able to use my knowledge of interferometry and apply it to exoplanet science. And the reason for this, like I said before, is that interferometry allows you to measure your star in a model independent way, which means most of your other stellar parameters, like luminosity and temperature, and linear radius, are also model independent because of the little equation called the Stephen-Boltzmann equation. And if you have your size of your star, your temperature of your star, your luminosity of your star, and the distance, you can do a whole lot with that. That is almost every fundamental parameter of a star that you need. And with that, you can use that and you can refine the other 2, which is your age and your mass, because those are not very easy to measure of stars. But you can model for them by using your directly measured properties. And so with those directly measured properties, you can constrain those models and you can get more precise and accurate measurement or estimates of your mass and age of your star. And if your star happens to have an exoplanet, you can also further constrain those exoplanet properties because pretty much every single exoplanet property that we know of is a direct function, or it's directly related in some way, shape, or form to that of the host star. So if you want the radius of your exoplanet and then just observe the transit, like that test, you need your stellar radius in order to get your planetary radius. If you have a radial velocity planet, you also need the mass of your star, mass of the whole system, and the mass of your star to do the mass of the planet. So pretty much every single exoplanet property is directly related to that of its star. So if we can remove all of that model dependence on those stellar properties as much as we can, that means we are pretty dang sure that that planet is exactly what we're saying it is, or that planet is exactly this size, or so on and so forth. So that is the power of this interferometry technique, is that if you can constrain these stellar properties and make them model independent as possible, that means your exoplanet properties are really, we're pretty sure. Like we're sure already, but now we're really sure that this is the answer. Of course, there's always room for error because science is ever evolving, and it's really hard to actually go to another exoplanet with a ruler and be like, all right, this is the size of it. Can't really weigh them either. So we rely on models. We have to, but by removing as much of that dependence as possible, you get pretty decent parameters. So that is what I do. I am studying two systems. They are both hosts of transiting and radial velocity planets, and I like to say that I held this to be the most efficient way possible because I have 2 stars and 9 planets. Lots of planets there. A lot of stellar systems only have 2 or 3 planets. There's not a lot of stars with more than 6 planets. I think there's only 13 of them. There's not a lot of very large planet systems out there that we've been able to find yet. Roman will probably change all of that. But I study HC 219124, which hosts 6 planets. It is a K-dwarf star, and it's also less than 10 parsecs away, so it's really close to us. I will be studying HC 158259. This is a host of 5 planets, and it is less than 100 parsecs away. So these are very close stars. The K-dwarf star with that many planets and being that close is also makes it really a hot topic of astronomers to study. It's been very well studied, but no one has actually combined all of the data that exists on this system into one kind of global fit and use charts, measure angular diameter, and all sorts of stuff. So I've spent quite a while developing a whole bunch of this. I'm currently running the simulations on my computer as we speak. Life of a grad student never ends. And then I have not touched 158259 yet, but this one is not as well studied. So hopefully it won't take me years long, but we'll see. It probably will. So some other results that I've done. This is an example of a visibility curve. So when I'm saying that you take some visibility data and you plot it and you fit it, this is what this looks like. So here we have on the x-axis something we call spatial frequency. That is just lambda over b, so wavelength of observation over your baseline. And then on the y-axis here, you have those visibility square measurements, and then this dashed line is that visibility that big equation. That is that equation plotted with the parameters it needs to be. And so all of the data here in black here are it's bin data from the PAVO instrument. So PAVO is a really cool instrument because for every one observation you take, every one time you look at a star and you're like, okay, I'm taking data, instead of just one data point, you get 15 because of the nature of the instrument. So it spectrally disperses across a bandpass across the bandpasses between 650 nanometers to 930 nanometers. So it covers a pretty wide range of wavelengths in the visible. And so for every one observation, you get 15 data points. And so if you take a lot of observations, which you should, because you're astronomer and you're going to take multiple data points, and you should, you get a lot of data. I think there's something around 300 data points in the light gray in the back. So in order to visually see, I just binned it and made it look a little prettier. The green points up here, this is from an instrument called Classic. I did not take these data. I didn't take any of this data. This was archival data. But anyway, I fit it and got an angular diameter of 0.45 milliarc seconds For context, that is a precision of 1.3%. So, yes. And so 51 Eridani, I forgot to introduce this star. 51 Eridani is cool. If you're interested, you should definitely look this star up. It was one of the first stars to have its planet directly imaged by the Gemini Planet Imager. So it has a fun little family portrait of the star and the planet going around it. It is a very young star. It is a member of the Beta Taurus moving group, and this group is a group of very young stars that are very close to us, like within 10 parsecs of us. And we like these groups because we can really figure out how old these stars are. One, they're close to us, we can study them really well. And so from interferometry, we get the diameter, the radius. For this star is about 1.45 times the size of our sun. And like once again, the precision level for the linear, the physical radius is 1.4%. So I can tell you that this star is this. I'm 1.4%. I know that this star, like, that's my error right there, which means that my temperature and luminosity measurements are also very precise. So I'm pretty like I'm 99 point whatever or % sure that the temperature of this star is 7,422 Kelvin. And same with the luminosity. And we model for the age and mass as well, because of course we can't do everything. And this star is 23 million years old, so it's very young in terms of the universe. And it is about 1.55 times this mass of our sun. So now that I know everything I need to know about the star, I can do stuff with the planet, and because it's a directly imaged planet, I'm very limited to what I can do with the planet. But what I can do is that because it's a young star, which means the planet probably formed around the same time as the star, we can assume that the planet is the same age as the star, relatively. And I can model, and this is an example of some of the plots that I did to get the mass of the planet, which is about 4.1 times Jupiter, or times the mass of Jupiter. So it's a pretty big planet. It's a hot Jupiter. And so the conclusions of this paper, so I published these results. It got accepted, and it's out in the journal finally. And measured stellar radius within a couple of % for time, mass, and age, and also got the mass of the planet and the age of the star. And with that, I can also point to what type of planet formation that this planet followed. So we concluded that we couldn't conclude which form yet in this form data, but we're pretty sure that it's either the hot start formation, which is disk instability formation. I could be wrong, please don't quote me on that. And then warm star, which is a new planet formation model that's been recently developed, which is a spectrum formation. That's probably the spectrum. All right, so this is where the really cool stuff is. Okay, so what can you do with interferometry other than what I do? So I do stellar diameters. I made these plots. They are HR diagrams. Now, what's cool about this HR diagram here is that every single data point here has been directly measured in some way, shape, or form. So we have been able to directly measure 693 stars, current as of December 2023. And you can see how widely distributed these stars are. So the majority of these stars have been observed with interferometry. A lot have been observed with, there's maybe about 30 or 40 that were lunar occultations, but the majority of these are stellar interferometry. And so for context also, this is just the HR diagram. We have the sun here for context. The size of the star, the size of the data point is relative to the size of this star. The color is corresponds to the temperature and spectral type. I also made this custom color map, which took way too long, but weirdly enough, a custom color map does not exist for astronomy. Don't know how. Yes.
On the first slide, those larger dots in front, does that show us the distance between the stars, like the red stars that are larger and the blue stars that are smaller?
No, it doesn't. It's just the order in which they got plotted in. But if you're interested, I made a 3D version of this plot, and it is fun. I don't have a demonstration, unfortunately, but if you go to tar.gsu.edu and you go to their stellar diameters page, you can play around with the 3D version. And the 3D version, the z-axis is distance. So the farthest star away that we've been able to measure is, I think, about 2,200 parsecs away. Yeah, it's a big star. But yes, and then so this is just kind of, very visually pleasing. This one I pointed out some famous stars. We have Sirius, we have Vega, Regulus, Bellatrix, Rigel, 5523, Alpha Centauri, Proxima Centauri. So this is just showing some famous stars, maybe stars that should be pretty well known to a variety of people. There's also two different versions of this plot. I'm really proud of this. It took me forever to do, but I'm very happy with how it turned out. Okay, so now off to the stuff that I do. So with interferometry, they also study rapid rotators. So these pictures here, and I'll try to get it out of the way here. These here are the actual surfaces of Regulus. I'm not even trying to pronounce that. Altera, Aldebaran, and Vega Max. Those are the actual surfaces. That is the surface of those stars. Like, that is not just a picture and like a bunch of colors. This is the surface of those stars. Insane. Like, by a couple 1 meter telescopes. Not a big fancy James Webb telescope, not a like multi-million dollar space telescope. These are ground-based telescopes in Southern California with a couple 1 meter telescopes, and you can see these surfaces. And that's not even the coolest images. So they done a lot of studies of rapid rotators. Now Rachel, Dr. Rachel Rodenbacher, she's at University of Michigan. She is a absolute just boss at all of this. These are, once again, the surfaces of the star, but these are the star spots. So not only can we see the surfaces, which is like pretty cool, awesome, she's able to map the star spots on these stars. So we can see the star spots on the sun because the sun is right there. This star is Zeta Andromeda. I don't remember how far away it is, but it's not our sun. It's not up in the sky that we can see every day. She's able to map the star spot locations, and in fact, like, was able to see that there's a persistent polar star spot on this star. This is the difference. So this set of plots was taken in 2011. This one was taken in 2013, and so you can just see the clear differences between about 2 years of imaging. So you have that persistent one, that's common, so it's not kind of pretty big. But then instead of just one star spot, we have about 1, 2, 3, 4, 5. And that's just a span of 2 years. And these are like different orientations. She also has GIFs of these, like on the website. So you can see it like rotating and like not just flat pictures. I couldn't get the GIFs on.
So we have pictures of a rotating star from however far away, way outside of our solar system. Like an actual like ball twisting around in space, and we can watch how it changes.
That's cool.
Oh yeah. And she's like the leader of this stuff. Like, she's done some insane work on this. I just like picked some of the really like visually striking ones. And the GIFs on the website are really cool to watch as well. All right. Also able to look at supergiant stars. So this is oh my gosh, RW Cepheid, able to see. All right, this is in December 2022, and this is July 2023. Much different shape. Like, I know it's not as pretty as this one. I know, but different instrument, different configurations, different everything. But you're still able to see how much the surface changed in about 7 months. And so they're actually also tracking Betelgeuse right now. They do the best to observe Betelgeuse when they can. And also do supernovae and novae. Able to image the fireballs after novae after exploding. Insane. I know, like, I'm hopefully you guys will feel like this is like wow as I am whenever I find new stuff out. So for example, Gail Shaker, she's the director of Chara. She also has done some amazing work. She observed, this is Nova Delphinus 2013. So this image here is 3 days after the explosion, 5 days, 7 days. So this was a target opportunity. They're like, hey, this thing's exploding. Screw everybody else. We're observing this, and able to get not just data points of brightness and angular diameter, but actually able to reconstruct the images of the fire. That is not a star. That is a fireball after a star is exploded. Crazy. I know. remember also there's binaries. This is real. This is the binaries in orbiting each other. This is not modeled. This is real. Like insane, right? And so this is able to resolve eclipsing binaries, and then also able to do astrometric orbits. So able to track the orbits of binaries. Also, they're starting to be able to track orbits of planets with astrometry versus anything else. But yes, this is the interacting binary data library. This is images. This is
that?
it's reconstructed from interferometry data. So it's not like someone's reporting this. But it's still real data. This is not modeled. This is just the reconstructions of all the data. I will caveat to that.
Are you saying a transfer? Is that little bridge between the two, and that's
That's
just stealing around?
That's what they think. Yeah.
Let's go.
I told you. It's really cool stuff at the end. And then also, this is my best friend's work. She's also cooking by. This here is the inner AU. So for context, from here to the sun is 1 astronaut per unit. This is the inner AU disk around a star. And they're able to resolve the disk itself. So instead of having like one big circle, which is the star and the disk, this is the starlight's been blocked out. This is the planet-forming disk around the star. So that is the stellar material, the circumstellar material that is around the star. And she observed it in several epochs. And there's a feature here. They didn't know what it was, so I'm not like I can't tell you what it was because we don't know. But it moved. So this is 2 different epochs. I forget how far apart. It wasn't anything crazy like a couple years. Like it was like a couple months, I'm pretty sure. But this feature improved quite a bit. And then this circle here is about. I'm pretty sure that's the size of our sun. And that's just for context, but able to image in our AU planet forming disks. When she showed me this possible for the paper with published, I was like, what is that? That is insane. She's like, I know, we weren't expecting this. And that is all I have. Some really cool stuff. I will take questions, and hopefully you're super excited about interferometry. You should definitely go check out the CHAR website. That's where most of these images came from. But CHAR itself is really cool. So is VLTI. VLTI is doing really cool stuff also. They're actually able to do planet imaging now using something called vortex fiber knowing. Don't really know how that works. But all the interferometry, like CHAR is not the only interferometer, it's just one of them. That's fact. So thank you, and I will take any questions.
I have a question about data groups, that there's different diameters all over everywhere. It obviously has a very, very large atmosphere. Does that affect your interferometry when the star has a very pronounced atmosphere?
So we just have to take into account more of like, so when you figure out what wind darkening coefficient you have, that kind of helps describe the atmosphere, because the wind darkening coefficient is determined with atmospheric walls. So you input a lot of your stellar parameters, and so it does affect it, just not as much as like I feel like you think, because what we're actually, whenever we measure stars, we're not measuring like the solid material in there. We're measuring what we can.
It's not individual, but when they have a strong atmosphere, it's kind of hard to tell.
It disperses a lot more. Most of that is taken into account with the wind darkening coefficients. And I know I talked for a really long time. I am so sorry.
That was awesome.
Okay, cool.
Mesmerized.
I know I went way over, but I just had a lot to. I love talking about this stuff, so I do apologize for running way over time.
Now, I do have a question regarding light time. When you were looking at a star as large as Betelgeuse, the light that left the edge of the star gets to you about 15 minutes later than the light that left the center of the star. So does that blur some of the data you're getting?
That's why you take multiple observations across multiple nights. It's like a lot of the anything that would kind of affect like a single telescope observation, they've taken into account by the types of observations that we have to do, like the style of observations. So by taking the multiple calibrators, multiple nights, multiple baselines, we can kind of calibrate as much of that out as possible, because it does affect it. You are right, but it's also a lot of that is also taken into account that we do have those delay lines. There's a lot It may seem simple that you just observe it with a couple telescopes, send it down a few optics lines, but the math and the engineering that went behind this is like, I still don't fully understand it, and I would very much applaud the people that were able to figure this out. But most of it's just, that's just why you take multiple data points, you get multiple, that way most of it's more like an averaged out number at the end.
So just a real quick question about the delay boxes. I'm trying to get my head around this because this seems insanely complicated. So I get the idea that one light's going to get a little different from one scope to the other. Do these delay lines have to shift over the course of the night as the star?
Yes.
Yeah. So it's just much more complicated.
Yes.
Yeah.
So for example, when I was there and I took data with the Pavo instrument, when we're trying to lock on to fringes, and by when I'm saying lock on is that we're trying to get the optics in the lab, like the parts aligned at the perfect position to combine the light. We're good for about 5 or 6 minutes before things start moving, and that's really just how long it takes to take the measurements. But as we're taking data, we are literally moving the carts, we're controlling the carts, and just by like millimeter by millimeter.
Okay.
Like it is, yeah, it's just.
So is this a constant change? Like, are you trying to figure out like, okay, it's moving at this rate, so all the mirrors need to be moving all the time, or is it one of those like 5 hours later you go adjust it to the 5 hours?
Most of it's been coded in,
Okay.
so it automatically adjusts it. And of course, like we'll go in, and if at the end of the night there's the software that we use to plan our observations, you can actually see when the stars are going to be what we call things away, which means we're able to move the carts enough to like be able to observe the star. Yeah, it's.
So there's a range out of which, like, you can only image a certain part of the sky, otherwise you won't be able to calibrate. That is incredible. Thank you.
I don't want to understand exactly how it's done. So essentially, you're taking a measurement at a specific frequency, based on, I guess, the fringes and the distance, or because you can't really get from one fringe to the other, how much it changes, to give you a distance and a diameter at a given frequency. And then comparing the distance and diameter at another frequency, eventually those interpolate to a range of distances and diameters.
So you're close. So in order to get a diameter, so the plot that I showed with all of those data points, each one of those data points is, that is just, when you go through, you have your raw fringes, you have all of your raw data, like completely, you just took everything, recorded it. It's absolutely meaningless until you go through reduce and calibrate. When you go through the reduction and calibration steps, so like for atmosphere, for instrumentation, what it does at the end of like the last step of all of this is that you're recombining it, but you're combining every single night of data that you took. So if you took 20 data points here, 20 data points here, 10 here, 5 and then like 2 years later type thing, all it does, it doesn't matter the time that you took it. All that matters is that you know the baseline, the wavelength, and that visibility squared number. It doesn't matter the time. You're not calculating the diameter at each. Like every time you take an observation, you're not calculating the diameter. It's really hard to just calculate a diameter off of one data point.
So you need the diameter at it.
Yeah. So the distance itself. So there's the baseline between telescopes, and there's the distance to the star. So the distance to the star, that's pretty constant. That's not. I mean, it'll change in a couple thousand years, but it's not going to change between now and everything.
So what actually causes the fringe? It's the edge of the star.
So
light comes from the star to where space and there's no light.
Yes. So what causes the fringes is that, just imagine, I think a better way to kind of is imagine that you're shining a flashlight at a telescope. Like imagine you're shining a flashlight. It's not a star. A flashlight is like really, really far away at these telescopes, and you just have light. You're just collecting light, and the light is sent down these tubes. It's just being sent down. All it is just it's collecting all of those photons from that star, and it's sending them all down to the lab, and then it's recombining all of that light. And so the amount of light that's there, that power equation that I showed several slides ago, that's telling you how much light has been taken at that time, or at that measurement, or across the several nights of observation. So it's telling you all we really care about is how much light did you observe, how far away your telescopes were, the wavelength of your observation, And then you just, like, there's a lot more math that's involved that's even, me trying to work through it, it's not as intuitive as I wish it was. The equation was developed by this guy, his name, last name's Hamburg Brown in 1974. This guy figured all this out, and he's used it ever since. But for reference, all that matters is just, it's like if outside when you go to observe a star, all of the light from whatever object you're looking at is hitting the telescope, and so no matter how much light, it's just, all of that light from that object is hitting that telescope, and you're reconstructing that image. So that's all that really matters. Hopefully that helps. Okay. Any other questions? Cool. Well, thank you. If you guys have any more questions, feel free to let Scott know, and he can reach out to me, and I can do my best to answer.